Okay, so a pretty tough topic here in calculus, related rates. The reason it's rather tough is because you can't really teach someone how to build these sorts of problems. It's all about understanding relationships and geometry and things like that to build the equation and then use calculus to solve the problem. So I have a problem here that involves related rates, and if we look at it, we have a ladder standing straight up against the side of a house. The base of the ladder is pulled away from the side of the house and at a certain rate. So we sort of have a picture like this. That's the side of the house. This is the ground. Here's the ladder. And the idea is that the ladder is sliding down the house because we're pulling the base of the ladder this way at 2 feet per second. So the interesting thing is this rate at which the base of the ladder is being pulled is not necessarily the same rate as the top of the ladder sliding down the side of the house, and this is what we need to figure out. Okay, so we've already sort of got this idea here of how to set this up. It's a good idea to draw a picture. Okay, so let's go back now. When we draw this this picture, we want to make sure what we do is focus in on what's important. And what's important, of course, is this triangle. And the idea is we want to label all the things that are changing, right? Related rates. They're rates because they change with time. So clearly, this is some moment in time after the ladder has started sliding, after it started sliding and before it hits the ground completely. So that's a generic picture at some moment in time while this action is happening. And in this triangle, we have this horizontal distance the base of the ladder is from the wall, so we'll maybe call that x. And the distance the top of the ladder is from the ground, let's call that y. Now notice both of these things are changing with time. So in our picture, the things that are changing with time we will label with variables. Now we have one more piece of information, and the ladder is 14 feet long, so this is a constant. So this thing's not changing, so I'll just label it that way. So the first thing we want to do is draw a generic picture. What I mean by generic is we don't know necessarily what x and y are. They're changing, so we're representing those parts with variables. So draw a generic picture sometime in the middle of the action. So in this case, the ladder sliding down the side of the house. It starts completely vertical, completely up against the house, and it ends on the ground. So my picture here is sometime in between that. Okay, so draw this picture. Now, the second thing, and this is the most important part, set up a relationship between the variables. This is the hard part. That's what you have to come up with. Okay, this is an equation. So when you go to set up your equation, there are lots of things that you can use. You may use, in this case, we're going to use the Pythagorean Theorem. You may use other triangle stuff like area or perimeter or something like that, or any geometry, as a matter of fact, for volume, area, perimeter, things like that. You may even use some trigonometry. So it sort of draws on all of your knowledge to build this equation, to understand the relationships between the things you see in the picture. Okay, so in this particular case, the relationship between x, y, and 14 is the Pythagorean theorem because this is a right triangle. So x squared plus y squared equals 14 squared, which is 196. So this equation was not terrible, okay? So now what do we want to do? Well, we need to plug things into this equation to solve, but you notice in the original problem we have these rates. Okay, and the question is, at what rate is the top of the ladder sliding? So this equation has no rates. So to get rates into the equation, we're going to differentiate. And typically, when we differentiate, it's with respect to time. WRT means with respect to, because they're rates. You might have feet per second or miles per hour or some change in angle per minute. The per minute, per hour, per second, those are all time. So typically we'll differentiate with respect to time. So that's what we'll do now. I'll take the derivative. I'll implicitly differentiate both sides with respect to time. And notice that x and y both change with time. So they are functions of time. So we have to use the chain rule as necessary. So the derivative of x squared is 2x, but by the chain rule I need to multiply by dx dt. Then y squared, the derivative is 2y dy dt. And the derivative of 196 is 0 because it is a constant, of course. Great, now we've taken our relationship, we've turned it into a rates relationship, and now we can try to solve the problem. The way we do that is we plug in data from a specific moment. So in this particular case, I am looking for dy dt. That's the unknown, right? At what rate is the top of the ladder sliding down the side of the house? So I'm looking for dy dt. So note, dy dt should be negative. The reason for that is y is decreasing as the ladder slides down the house. So the rate at which y is changing is a negative rate because y is decreasing. However, dx dt is being pulled this way. X is increasing, so dx dt will be a positive number. In fact, we know that dx dt is 2 feet per second. Okay. It's also very important when you solve these problems that all of your units match. So every place you look in this problem, your distances should be feet and your time should be seconds, and they are already for us, so we don't have to worry too much about that. So we know dx dt is 2 feet per second. It's a rate, 2 feet per second. We don't know x and we don't know y, however. But what we do know is the moment in time, the specific moment we're talking about in this particular problem is 2 seconds after the base begins being pulled away. And we know that we're being pulled away at a rate of 2 feet per second. So let's look at another right triangle. So this is our generic picture here. Now at a specific moment, at this 2 seconds mark, we still know this is 14, but if x is moving away from the side of the house at 2 feet per second, and it's done that for 2 seconds, it's traveled 4 feet, right? So x would be 4 feet at that specific moment. The base of the ladder would be 4 feet from the house. And then we use the Pythagorean Theorem to get this side, which would end up being the square root of 180. So now we know x is 4, dx dt is 2, and y is the square root of 180. Now we have all the unknowns except for the thing we want to solve for, so we can just apply algebra to solve for dy dt. So I'll subtract this x stuff and divide by 2y to get dy dt by itself. So I subtracted 2x dx dt, that's the stuff you see on top, and I divided by 2y, which is 2 times the square root of 80 on the bottom. And you can see that's going to be a negative number. And we should get something like negative 0.596. and that's a change in y is in feet, time is in seconds, so this will be feet per second. So at 2 seconds after the base begins being pulled away, at that moment in time, this specific moment, the top of the ladder is sliding down the wall at this rate, negative 0.596 feet per second. And the further away x gets, the vertical change in rate is going to be different than this. So the rate of change of y is going to be changing. So that's why it's very important to look at this specific moment in time. And that is an introduction to related rates, using this Pythagorean theorem problem as an example of how to do it.